tried some new methods to see, have we captured the range, right? And then as well as part of the distribution would be the weights that we start to associate with that. So Bob is going to now try to start to address this in a more traditional way of how we captured the range, but I think that the tools Nico has just showed us is going to be another way to sort of push the bounds of those approaches.
Yeah, this is sort of to begin. Are we switching screens now? Or are we, which way do I point? If I point, which one, does this move? So I think one of the important, this is sort of more of a discussion section rather than a presentation. I just have some slides to illustrate them. But I think one of the important things is what both Brian have shown and what Nico have shown. They've all started with a set of models and then mapped everything, and it's all falling within the boundary or extrapolated out from those models. And so the question will be, do we have enough starting models to build our uncertainty space out of? So this is just some figures illustrating ranges of the models we're considering, and then the question will be to the audience, there's the things we're not capturing with these models now that should perhaps be brought in. And these slides are not there. Okay, you didn't? Okay, it's now event. So I have some plots that are basically somewhat of a repeat of what Nick showed this morning, but perhaps a little easier to see. And they're not specific to any of the sites, they're more generic. But I basically plotted the range of predictions of NGA, just for historical reasons, NGA West 2, NGA West 2 plus Linda's epistemic model, adding uncertainty into that range, plus the other 4 GMPEs that we have in our candidate range. And we've shown response spectra for specific scenarios and magnitude and distance scaling. So this is, if you remember Nick's plot this morning, we were looking at magnitude 7, around 10 kilometers. So on this plot, we have the, what was salmon and R, and what color it is right now, sort of yellowish. This is the range of the predictions for magnitude 7 at 10 kilometers strike slip from the NGA West 2 models. And the blue line is the added epistemic uncertainty coming from the model of Altec and Young's, basically looking at the uncertainty in the medians of each model and adding that to expand the range. The dashed black lines are the range of NGA West 1. And then the 4 colored curves are the predictions from the 4 additional models, Acker et al., Bindi et al., 2011, Grazer and Konkalkan, and Zhao et al., 2006. Just linear and then log space so you can see the low frequency part. So you can see from this, that straight lines like this are just lack of points between frequencies. But there are, there's been a shift in the range of NGA West 1 to NGA West 2 in the range of prediction in the shape and where the peaks are. The amplitudes have shifted a little bit, and it's capturing most of the range of the other 4 models except for Grazer and Kalkin in this case, which is higher here in the low frequencies.
Can you point out the difference between the Bindi and the Zhao? Because I can't tell the color differences.
Okay.
I think the Zhao is a taller, is a higher one, right?
Zhao is here. Because they don't have high frequency, they have just 0.5, and then they have PGA, and then it's up to you to pick where you want to put it. He plots it at 0.02 on his figures, but basically I just drew a line between them. So this is Zhao, and this is Bindi here with. So just to keep all sites happy, I plotted the results for what will probably be important for Palo Verde, which is a magnitude near 8 at a large distance, 200 kilometers here. So this now Bindi, this is the scaling that coming out of Bindi 2011. Like saying right now, we've recently got a preliminary version of Bindi 2013, or I don't know if it's final, but there's still, I think, some tweaks that are working on it. But anyway, it resolves a lot of these issues in terms of the scaling at large magnitudes. Not completely, but in most cases, it gets rid of this strange prediction. I haven't plotted this one all the way out, but this is at 200 kilometers, and it's higher. It sticks up much higher because Nick was plotting a 7.5, and this is an 8. And then you can see the range of NGA West 1 went much higher, and as many have acknowledged, that the distance scaling at large distance from NGA West 1 needed some work, so that the range is now lower. And you can see they're falling in here, and then the Ecker et al. And then the question really is, does it go work all the way out to 200 kilometers and to magnitude 8? So there's, I plotted everything as far as the range, and then the questions are, some of the range is too far. This is a figure showing the hanging wall predictions again, for the same set of models. NGA West 2, NGA West 1 in black, and then the epistemic uncertainty in NGA West 2. And then the 4 models, some of which, or many of which, don't really address hanging wall explicitly. And this is plotted including the range in NGA West 2 includes the model of Idris et al. But Idris doesn't explicitly address hanging wall. He doesn't say that it doesn't exist, he just doesn't really address it. So if we take out Idris from that range, then the range narrows and comes up, such that these models are all sitting higher than the predictions pretty much from the other models. This is the same thing, excuse me, for a normal fault on the footwall side at 15 kilometers, predictions from the range of models, NGA 2, the other models many of which have a lot more normal faulting data in them than NGA West does. But you can see there are not really any large models sticking out here. And then, again, Idris doesn't really address normal faulting in his model, so I took it out, but it makes almost no effect because his prediction for strike slip fits in the range of predictions of the normal faulting from the other models. Then to expand this or show it in a different direction, these are magnitude scaling plots, but they're plotted a little different. They're centered on magnitude 7. So if we can fix the value of magnitude 7 at 10 kilometers, how does the scaling go up and down from that point? And just again showing the ranges from NGA West 2, which is the yellowish color here, the expansion of the uncertainty above magnitude 7 because there's a magnitude term on the epistemic uncertainty model. And then we have the Bindi model shooting off here, and looking at the Bindi 2013, this large overshoot has been fixed. I think in most periods it falls back down in towards the range of the other models. And then magnitudes, this was at PGA, or 100 hertz, 5 hertz, 1 hertz, and 3 hertz. And all plotted on here, just for interest, is our initial interpretation of how we would implement Zhao and Liu 2011, working off of the Zhao et al. 2006 model, basically assuming no magnitude scaling above magnitude 7, what it would look like compared to everything else. So it's quite different than any of the other models at low frequency.
For these plots for magnitude less than 7, why don't you have an added epistemic uncertainty?
Because it's not
constant.
magnitude dependent anymore.
Yeah, but shouldn't you be having
no,
something
because
that
the scaling, the model set up, you scale everything up by the same factor,
Constant.
so the relative amplitude
Okay.
doesn't change. So it's only, there's only a magnitude, it would only be if there's a magnitude dependence in the epistemic uncertainty would you get a blue band. That's why it only shows above. At least in the way I implemented it.
Yeah, because this is the ratio, right?
This is the ratio of a prediction at 7 to the ratio at prediction at the other magnitudes. And the same type of figure for distance scaling. Again, for magnitude strike slip, it's fixing at 10 kilometers, how these models would scale in and out to larger distances. I did not go out to 200 kilometers because there's a lot of uncertainty, and that is all going to be, I think, addressed better by looking at the data from Arizona. So you can see this is Vladimir model, which this is anchored now, assuming that the value at 10 kilometers is known, and then how would it scale in? It would scale downward. And if you normalize this to 1 kilometer, then it would stick out. You know, it all depends on the normalization point. But
Bob?
typically, we have more data back here to anchor things,
Hi, Bob. Is there no epistemic uncertainty also plotted in these as well?
because there's no distance term.
Got it. Okay, thank you.
It's on here, but it's mapped underneath there.
Okay.
And the same for now at longer periods, 1 second and 3 seconds. You can see that there's a little bit tighter, that the NGA West 2 has dropped at long period compared to NGA West 1. In close, it's pretty much the same as before at long periods. And the other models are spanning a range from across that. So they are wider distributions for distance scaling in those models compared to NGA. So those are the points, and I think the takeaway from that is that perhaps we need to look at putting these other models into some process of looking at the range that we need to be evaluating for developing our model for these projects, as opposed to just taking the NGA band itself. We need to expand the consideration of additional models. And that's as far as I got with it.
So I think it would help us to even get on here what the simulations would look like, right? Because we don't have that, to see if that is, as well would map out a different solution space. Because here you're just doing it, this is scenarios, so we can pull those out easily. Nico, you have to have the entire vector defined, right? So
well, I could actually adjust the vector. I mean, I don't need everything. I mean, I can also use just if we have.
I think we need a
Yes.
subset
Yes.
probably to try to work through.
It doesn't really change that much if I use. So, for example, if I use only magnitude in 0.5 bins, the visualization doesn't change that much. So it doesn't have to be this very 1,000 points in the vector. It can also be just 100 points or something.
But part of our burden, is which of these models do we want? You know, we can expand it, but how do we determine which of those really belong? And is that checking with California data? Do we see if it's, as opposed to fitting that data, is it at least not inconsistent with that data? That kind of a question. Have you thought about that part of it?
Well, what I was thinking about is is trying to construct models from the self-organization map and see what those models look like, and are they, if we construct a model that say fits in a square that in a cell that's out in the middle and no one is away from all the other cells, and then look at that model versus data and see if, does that model make any sense relative to data? Is it a model that we need to bring in? It'd be one way to try and use the self-organization maps to, or even the simulations from, what that Brian is supposed to fill out the space, and then we need to look at what those models look like in the space versus strong motion data and see if it's something we need to bring in. Weekends work.
Other comments?
Very long weekend.
Tom?
So there's another community of people who do parameter estimation, and they don't seem to be in this room, but down the hall from me is Professor Jim Beck, who forces all my students to go through Bayesian analysis. And if he were here, he'd be jumping up and down and saying, where are your priors? And so the Bayesian persons would say, if there are different ways to fit data and the data doesn't really constrain what you're doing, you also need to put in that thing that we call, is it reasonable, or make judgment on it. And typically that's formally put in the logical process as a Bayesian prior in the model. And for instance, these fits with numerical simulations, depending on how much confidence in different parts of them, would go into a Bayesian prior, and then you'd say, does the data require you to be different from what your understanding is? Is that, as opposed to saying, I'm ignorant of the Earth and I'm just going to look at data and let it tell me these scaling relationships. So the other group of statistical analysis who do parameter estimation, I mean, I think they'd be pretty upset that there wasn't some Bayesian prior in all of this analysis.
I think we probably treat that in a different way than you're thinking. I mean, it's buried in what we're doing. We're fundamentally not doing fitting curves to data. We're building a model with our prior is constraints that we're putting on the scaling and so forth.
I think I agree with that, but maybe we're kind of struggling with, we're not being very formal about how we're
So part of what this can let you do is you could set up the models that could be candidates here, and then there's one is our prior is what we started out with, and then we're going to push them around that, yet checking with the data to see are those models, new ones, rejected by the data or not, right? And if we're back to, instead of them fitting the data, are they not inconsistent? I mean, that kind of a test, and to see how far we can push them out, yet eliminating ones that don't make sense. So it's not too far off, but I think it's less formal than what you had described. Sure, Gabe.
A couple of comments. I agree with Norm that the prior in many ways is specified by the functional forms that are using the regression, because that way you are forcing relations between the GMP, at least in that sense that you are forcing the relationship between GMP values at different magnitude distance combinations. That's comment number one. Comment number two, I guess, aren't we getting into a situation where the data are being used twice? Once to fit the models and then to assign weights?
A little bit, but one it would be those other models which were from very different regions, right?
Mm-hmm.
Almost independent.
Okay.
And now is the, let's say Akker's model, is that consistent or not inconsistent with California data? Close in.
Okay.
Okay, so then I can check that, and we're not using it twice. there's a little overlap because we took some European data and used it, but I don't think it's a full
Okay.
overlap of the problem.
All right.
But we do have to be careful that we're not getting ourselves into a circle here.
Because that way you reduce the uncertainty pretty quick.
Sinan, do you have any comments about whether the models you have would be considered applicable to California?
I mean,
Use a microphone.
do I have to say my name? Okay, so this is Sinan Akkar. Norm, we tested our ASP model with the Iranian data, Turkish data alone, Greek data, and the results are quite, consistent. They can, the model itself can be applicable to those countries.
So it's essentially a globally applicable model at this point.
Well, yeah. Well, I may have some reservations because, essentially we have not done any testing with the Californian data, for example, data from California or from Japanese data. But for the rest of the world, shallow active crustal regions, we did it.
Anything else? Linda?
Yeah, I think it's a little bit misleading to just try to address the idea of, capturing as much as possible. And I think Nico mentioned this, that shouldn't you be thinking about what space you want to capture beforehand? As opposed to bringing in, one of the things, or at least I understood, is you need to think about where you want to be in the space. You don't necessarily want to be everywhere, right? So do you have any ideas about that?
I don't think we.
Because you might be somewhere where you don't want to be, right?
Can I just comment on that?
That's the whole question, is where do we want to be, right? What's the space that's technically defensible, which isn't everywhere on here, and how do we eliminate those that are not applicable from our particular application, yet still not undersample the range because we only had a small set of candidate GMPs to start with. So that's how do you do that? That's why we're all sitting here trying to and set the whether it's symmetric or asymmetric and all of those types of things. So I think we're starting with these candidate models, some of which are quite a bit different, and really saying, are these still, while they're different from what we derived from the California data, are they still not inconsistent with the California data, where we would say, that rejects the application of this model. That's our whole problem, though, is trying to set this range that is as broad as it can be and no broader, right? Or should.
Oh, Nico. Oh, PPRP first.
So I'm just saying this as a, not as a PPRP member, because I don't want to influence your judgment. The reason why I do this GMPE space, the motivation behind that is exactly what Linda has asked, is to provide a idea of where we want to be. Okay. So that's.
You mean this? You mean the space by the cloud of points? That the gray dot space?
Yes.
Yeah. That's why that's really helpful to see, are we capturing that or not? And
Yeah.
it looks like it's not right now. It's got part of it. Nico's a little worried we've reduced it to just a couple dimensions and not enough yet. Nico?
Well, this is Nico. There's some other thing I want to mention. We did experiments about that by adding more and more models, but the only thing you do when adding more models and then not really taking care of the weighting is you just center your distribution around the mean. This is when you add more models, you just you center everything around the mean of all the models, and the mean is, and this will be around this mean. And if you just add all the NGA sampled models, you'll just will be more and more
Sure,
confident in this particular mean.
But if we take on one problem, and that is define the range. Okay, and so we can use that to say, here's the space that we want to capture. Now the whole next part is the weights in there, which is our, where it's centered and where what is, if it's asymmetric or whatever it's going to be at that point. But I think we have to take those as two steps. One is just what's the range we would say are credible, and then how do we assign the weights within that range?
Well, if you're open to running a hazard using 1,000 GMPE, you don't have to worry about weight.
No, because you're trying to say one area will have more samples, so it gets a higher probability. Yeah. Any other comments on this topic? John, is it all making sense to you now? No? Yes?
Well, sort of. The part that I still struggle with is understanding the physical meaning of moving off in different directions within the cloud. There was a plot yesterday where changing the magnitude up and down, the distance up and down, puts you on a straight line, right? So that I could kind of understand. But then there were plots today where the line actually bent.
Christine, you have to talk into a microphone if you're going to. No, I think that's a great comment still. It's still difficult to understand exactly what's there, but once you map it out and you say, let me go now pull that GMPE back, because he can pull back the parameters, then we can look at it in a space that you're normally looking at, and that
Which
might
is
be
good,
the way to do it.
Yeah, then we can make plots like these from
Right.
from the prediction. I mean, this plot can be made from the predictions without actually having to fit a GMPE to it, just from the the salmon's the vector that's in that cell.
We're always dealing with our basic problem we've had before is a set of published models doesn't span the space of possible models. And how do we fill that in? So that's really what we're trying to do here. And not only fill in between, but push it out a little bit in a different direction. Yet still not make something that is violating the observations that we have. Adrian?
When there are other parameters that control variability between models, for example, hanging wall, then you have to be careful about looking at directions only in magnitude, distance, space, because then you have to introduce those other parameters in there.
Yes. Sinan?
Sinanakar, ME2 again. If it helps, what we can do, for example, in my group, we can test Bindi et al. And Akar et al. Models, GMPs, with the database of California, using these methods of Sherbaum et al. 2009 or other methods, data-driven testing methods, methods.
But the difference is we're not trying to sort of rank them. We're trying to find a way to exclude a model. So that there's going to be a point that we're going to say it's too far off, right?
Okay.
Yeah.
All right. Just to give you an idea of how well those GMPs fit in the Californian data. I mean,
right.
I mean, for different magnitude bins, for different distance bins, that kind of thing. I mean, those are the things that I can really do fast because, I mean, I have enough resources for that. If it helps.
Right. Thanks. Christine, then we're...
Christine Goulet here. So I'm still a bit concerned that this is really useful, but I'm concerned on how we're gonna actually use that and cover those other issues like the effects of PS30 and this and that, and how we're gonna come up with a way to constrain what is the range really well, and then select the weights correctly.
So an approach is to follow our traditional way of doing the problem. And then as we
Test it
here
Okay.
and use this to give us feedback and come back several times. I think that's the
Okay.
state of this. It is new,
Yeah.
and it needs to be understood before it's pushed into practice to be driven things. But I think it can inform us if we've missed something. It doesn't make sense, and still go back to our traditional method in the end of creating a weight in the models, but continue probably a couple of iterations back and forth.
Okay.
In this kind of a space.
And practically, we would do that with PCA because that's the one that's computationally doable, right? Or
I think we can leave the computer resources as a separate problem.
okay.
You're near a big university. Computer time shouldn't be our limiting factor. There's solutions to that problem.
Yes, I'm
mean,
just trying to be practical about what can be achieved in a reasonable time.
Right,
If
right.
it's months of computer time,
then we
it's
can't do
gonna
it,
be
clearly,
something,
of course.
right?
And we need to find out some of that. But I think your concern is right. We don't want to jump in here and say this is going to drive our answer, but it should help inform us. Okay? And
So you will put the weights and then see how these things then map onto the full sample space. And we'll make a judgment.
right, and then maybe say, I really am missing something. Let me
Okay.
create another model here. We pull that one out and say, I need to add that to my set of candidate models to better set what the range is, and we're back to appropriate weights and so forth. And
I guess it's also for Nico. If you take one backbone and scale it up and down in various ways, do you cover as much as, I mean, how much would you cover if you would take one of these and scale it versus all 14?
Well, if you just scale it up and down,
But not just magnitude and distance, other things.
but then you're still only going in one direction.
But I thought you
So-
had two lines, one for magnitude, one for distance. Wouldn't you have other lines as well if you did other parts of the GMP?
Well, if you change like the coefficients of the GMP, then you would map out probably the whole space as well.
Yeah, a couple of comments. One, I think, and I think Adrian referred to this, it might be useful to do this analysis, but do it on a more local basis. For example, at short distances, do this analysis, but including things like hanging wall effects and so on. And at long distances, then a more traditional magnitude distance space. The other thought along that lines, one way to maybe bound from the other side the uncertainty, as Linda was asking for, is try to fit a less parametric model to the data that the project has. Again, maybe along the lines of what John Anderson did some years ago, and a model which has less constraints, less physical constraints, and that immediately will give you a higher uncertainty. And set that as an upper bound. Maybe it's not a useful upper bound. Again, a less parametric model will immediately give you a broader uncertainty, because you're putting in fewer constraints. Less parametric, maybe fully non-parametric. That's probably not practical because we know some things. We think we know what magnitude scaling, for example, and distance scaling. They tend to go in one direction, that sort of thing. Except, well, with a few counter examples. But that way, and I'm not entirely aware of all the details, but that's might be one way to get around that from the other side.
We need to be really careful about non-parametric fits to the models. I think what Sinan showed you, what he called the research models, was heading that way, saying, let the data do what it wants, which is great when you're after a problem in the center of the data range. We're going to be on the edges. So we're going to be on the hanging wall of big magnitudes at close distances. So
Okay.
that, yeah, it just won't have a constraint, so we have to bring something else. Now, if you run the numerical simulations where we've got huge data sets, I think you could take that step and push it through a non-parametric model, and it would be robust. But these hopes that the data will guide you when we are really, our focus is on extrapolation is a tough problem.
Okay.
With that, let's stop this topic because it's going to keep going on forever. I think I hope you all got a flavor of where we're heading with this and trying some new stuff. We talked about this several years ago. Some of you probably were there. And we're much further along than we were before in terms of getting a workable product.